Okay, so I'm going to talk to you today about groups, some of the simple properties of groups. And let me start with a definition of what a group is. You don't need to stand, right?
No, I'm just make sure it's all set up. Okay.
So basically, a group is a set of objects that have certain operations. And so the elements of the group are, let us say, F, G, H. The group is called G, and we often say F, G, H is in G. And the properties are, first of all, that there's an operation. And the operation between elements is called, conventionally it's called multiplication. And in reality, in most cases, it really is multiplication. It's matrix multiplication. And so you have F times G is in G. So in other words, take any two elements of the group, multiply them together, you get another element of the group that is in the group. In other words, Fg is equal to H, and H is in the group. This is called closure. And this is the only property that's tricky. Everything else is almost always automatic. Let me mention the other properties. Associativity. Well, F times GH is equal to FG times H. That's associativity. The third property is the identity. There is an E in the group such that GE is equal to EG is equal to G for all G in the group. So that basically is the something that acts as the number 1. And the fourth property is that there's always an inverse. For every G in the group, there is a G inverse in the group such that GG inverse is equal to E is equal to G inverse G. So these are the four properties that tell you whether a certain set of objects forms a group. It's a certain set of objects and an operation which is called multiplication. Now, one interesting thing about groups is that if you have any set of physical transformations, in other words, if you're such as to move something, or as we say in physics departments, to translate something in space or time, that is an operation that naturally forms a group. So, or if we rotate something, that's an operation that naturally forms a group. And the idea is that the product, so let's just say that T is a transformation of some kind, a physical transformation. And then you can say, well, you can multiply transformations. That means you apply the transformation T, and then you apply the transformation T prime. And of course, that's just two transformations, which is some other transformation, which would be called TW prime. So you have closure kind of automatically. That's the hard property. But you have closure almost automatically for transformations, or very naturally, almost automatically. The other thing is associativity. Well, that does turn out automatically because T double prime times T prime times T is certainly equal to T double prime T prime times T, because in both cases you apply this transformation, then that one, and then that one. Duh. So the parentheses really have no actual effect. The third thing is the identity. Well, the identity is that the transformation is just the identity transformation. In other words, that's what we would call E. It's the transformation where you don't do anything at all to the system. So that's intrinsically true. And then, if these transformations are reversible, and so many simple physical transformations on simple physical systems typically are reversible, then there's obviously an inverse transformation. You just undo whatever you did, and so T inverse T is the do-nothing transformation, and that's also the transformation followed by the do-nothing transformation. So it's in other words, if the transformation is move this thing of water this way, if that's the transformation, then the inverse transformation is this, and if you do the one followed by the other, it's just equivalent to not doing anything at all. So, let's see, I forgot to reward the person operating the camera. So in fact, physical transformations naturally form groups. The only part that might fail is closure. That is to say, if you have two transformations, is doing one after the other always one of your transformations? Well, in most cases that I think of, it's essentially automatically true. There is, however, a simple way to guarantee that, namely that you say your transformation has a certain characteristic, namely that it doesn't do something. In other words, it leaves something unchanged or invariant. So then you get closure automatically, because if T leaves some property invariant and T prime also leaves a property invariant, then applying the two of them will not change the property, and so you have a transformation that leaves whatever that property is invariant. So this is how many of the groups that we talk about in physics departments actually are defined. There is, for example, the rotations. The rotations, it's if you have, for example, some object, and then there's some particular point on that object, and you make any transformation of this object that leaves one of its points unchanged, then that forms a group. That's the group of rotations. And if the object is in some higher dimensional space, then it's a group of rotations in that higher dimensional space. Normally the translations don't leave anything invariant, because you're just moving the object from any place to any other place, and so there's nothing invariant. But in a sense, there is something invariant, because if the object is not a point, then the translation is one that doesn't change the orientation of the object. In other words, it's not a rotation. So a translation is anything you do to change the location of an object without rotating it at all. And of course, when we say without rotating it, we have in mind that we have a sort of an equivalence class of these points, so that anyway, you know what I mean when I say you move it around without rotating it. Okay, so that's the basic idea of translations. If we're translating points, then we can in fact say something though about these translations, namely that they leave the distance between any 2 points invariant. That is something that's invariant. We're translating all the points, then the difference between any two is invariant. And in this case of translation, the natural operation is the addition of vectors. In other words, T1 might be x goes to x plus a, where the arrow indicates that this is a multi-component vector. Could be 3-dimensional, could be 13-dimensional. And then T2 might be x goes to x plus b, and then we say T1, T2, well, T2, T1, say, takes x to x plus a plus b, and so the natural thing is addition of vectors. But the transformations can be more general than, obviously, than translations and rotations. You can have what are called Lorentz transformations. And these are transformations that leave a certain quadratic form invariant, namely, they leave the Minkowski distance. In other words, we have this metric so we leave this invariant. This is something that we normally call x minus y squared, and it's x minus y, the vector part, squared, minus x0 minus y0 squared. Okay, so, and this, transformations that leave this invariant are not only the Lorentz transformations, but in fact, the translations also leave this invariant, because if you translate x and y by the same 4-vector, the difference remains invariant. And so that forms what's called the Poincare group. Would you do me a favor, David, and run that blind up?
Sure.
Thank you. By the way, the Poincare in this case is Henri Poincare, and he was actually the cousin of Raymond Poincare, who was president of France during the First World War, so I guess he was a very unlucky president of France. Anyway, in the case of translations, whether you do T1 before T2 doesn't make any difference. But in general, the order of the transformations does make a difference. And so you can consider the commutator of T prime with T, and that if this is equal to 0, the group is said to be abelian, and then the order of the transformation doesn't matter. If it's not equal to 0, then it's said to be non-abelian. Mathematicians are nothing if not logical and consistent.
So we're doing group theory here, right? We're doing
Yeah,
group
we're
theory.
doing group theory. Now, I'm doing group theory because that's what Mr. Coper, right?
Yep.
Is it Coper or Copper?
Kappa.
Copper picked.
Okay.
But we can switch and do something else next week.
Sure.
Is group theory something you want to hear, or?
Well, I kind of did that a few semesters ago with you.
Yeah. All right. So let's not stay on group theory
Well,
forever.
or we can go at not light speed.
What?
We can go at a quick pace.
What topic did you have in mind?
Oh, I don't know. I had some
All right.
ideas.
Well,
but
I'll
I'll think.
And
Okay.
at the end of class, tell me what you'd like to switch to after group theory.
Sure. Because
And
I'm open to
I don't want to do.
Okay.
I don't want to try to do the whole chapter. I
Right.
think I'm going to try to do
Oh,
group theory light.
Okay.
Anyway, these are the two different kinds there, and Invariant is named after Niels Abel, who unfortunately only lived to be 27. I think he died of TB that he caught in Paris. And he died in 1829. Anyway, matrices naturally form groups, as I said, and the operation is matrix multiplication. And so if the matrices are non-singular, that is to say, if they have a determinant that's non-zero, then they have inverses. The question is the inverse will be in the group because it naturally undoes the operation of the matrix. And so the question with a group of matrices is simply whether the group is closed. In other words, if the two matrices are in the group, is the product in the group. And sometimes it is, sometimes it isn't. And typically, if the group is defined as those matrices that leave something or other unchanged, then those matrices will form a group. One group is the orthogonal group. That leaves, for example, x1 squared plus x2 squared plus xn squared. This group is called ON. Then there's the almost equivalent thing, the unitary group, where you have a sum of complex numbers. You leave this sum of complex numbers, the absolute value squared of the complex numbers invariant, and that's called the unitary group at n dimensions, UN. Okay, now, what we're normally talking about are continuous groups. And continuous groups, at least in a lot of physics, they're particularly important. But there are discrete groups that are also important and are particularly important in solid state physics because different crystals are invariant under various discrete sets of transformations, discrete translations. When you translate the system by the distance between two atoms in the crystal. Anyway, let's think about continuous groups here, and this is where the group depends upon a set of parameters, which I'm writing as alpha, and it depends continuously on a set of parameters, and these are this is called a continuous group or a Lie group, named after a mathematician. I think his name was Sophus Lie. And by the way, the order of a group is the number of elements in the group. So if you have a finite group, like for crystals, then you might have n elements in the group. On the other hand, in continuous groups, since these parameters vary continuously, you have infinitely many elements in the continuous group. And now, what we're often interested in is the representation D of G of these parameters alpha. So D is a matrix, and we always call it D from the German Darstellung, which is the German word for representation. We inherited, unfortunately, a great many German words, and we haven't managed to get rid of them. Anyway, I guess that's the nature of English, but the language is kind of like glue, and any foreign word that comes in sticks, which is probably a good thing. Anyway, D is a matrix that depends on the group element. The group element depends on the set of parameters. And the way in which the group element depends on the parameters is continuous, and implicitly I'm also going to be assuming, if I have never seen anything, any useful representation depends continuously on the group element and on the parameters. So everything here is continuous. And it follows then that there's a theorem that you probably were taught when you did, when you studied mathematics as a college student. Namely, that if you have a function f of x that's continuous, and then the magnitude of f of s is bounded on any closed and bounded set. So closed and bounded, for example, 0 to 1, where we mean all real numbers between 0 and 1, but including 0 and including 1. That's a closed interval. And you could prove, in fact, if you beg me and I somehow have a fit of intelligence, I might be able to prove why this is true. But it's a famous theorem that that a function that's continuous on a closed and bounded set is bounded on that closed and bounded set. A counter, the reason you might say, why does it matter to include 0 and 1? And it's curious why it matters. It's counterintuitive, but it's easy to see a counterexample. The inverse function, 1 over x, is continuous. But it's not bounded on the open interval. The open interval is 0 to 1, because you can get arbitrarily close to 0 and this thing gets arbitrarily big. And in fact, on the closed interval, it's not defined because 1 over 0 isn't defined. So that's the. All right. So the upshot is that when mathematicians talk about a set that's compact, by the way, compact means just closed and bounded. What mathematicians say is that a group is compact if the set of parameters is closed and bounded. But on the other hand, if the set of parameters is closed and bounded, then anything that depends upon continuously is bounded on the closed and bounded set. And consequently, something like this is trace of d dagger, and let me just write it as d dagger of alpha, d of alpha. This, you can say, is the norm of d of alpha, absolute value squared. This is trace, not h bar, okay? So this depends, this is a continuous function of alpha, and so if the space of parameters is closed and bounded, then this norm is bounded. And so that means that the mathematicians are not nuts when they say that when they define a compact group as one whose parameter space is compact. Physicists normally just say, well, that this is bounded for any set of parameters. So examples of compact groups, examples of compact groups are the orthogonal groups, because these are matrices such that trace of O inverse O which is actually the trace of O transpose O, is equal to just n if it's ON, because this is the identity. And similarly, the trace of U adjoint U for unitary matrices is usually the trace of I, and that's also n. So the group UN, ON, they're both compact groups. On the other hand, the translations are not compact because you can translate things in arbitrary distance, so that's not compact. And the Lorentz transformations, which, as you know, just mean that you change your reference frame from the one that's natural in this room to the one that's natural in a plane flying overhead. And those two, if you imagine the plane flies faster and faster, those transformation, the set of parameters is not closed and bounded, because you will say, wait a second, the plane can't go faster than the speed of light. So there is some sense in which the parameter space is bounded, but technically the parameters that do apply for the Lorentz transformation are not closed and bounded. It's in other words, the parameter space for the Lorentz group, which is the set of Lorentz transformations, those parameters are not the speed, which would be closed and bounded. No, it would actually not be. It's not closed, you see, because you never get to the speed of light.
Okay.
First, and then secondly, the parameters that you use normally, the ones that are the plethora of alpha, are not the speed. It's something else that we can talk about later. It's like a boost parameter.
Yeah, I said boost.
Okay, so there are other kinds of non-compact groups. Just for example, the set of all 2x2 non-singular matrices. This is non-compact. Or the set of n by n non-singular real matrices, or the set of all n by n non-singular complex matrices. Those are non-compact groups. And they may play a bigger role in physics than they do so far, but we tend not to like them very much. Okay, there's something that I should mention then, is that if the group is compact, then it has unitary representations, and if it's not compact, then it doesn't. Now, if you have a representation of this, there are typically equivalent representations. You can define d prime of G to be S inverse d of G S, where S is any non-singular matrix. And so this is an equivalent representation. So d prime is equivalent D. Okay, there's also, this is a little technical, there's a proper subspace of a vector space. There's a subspace of lower dimension. Well, that makes sense. But a proper space that's invariant under the action of a representation. In other words, if D of G maps all the vectors in some space W into W, then this is said to be, then W is a proper invariant subspace. And so this is how the mathematicians distinguish reducible and irreducible groups. If there's a proper invariant, so this is a proper invariant subspace, That's W. It's proper because it's not the whole space, and it's not zero either. And it's invariant because the transformations just move these vectors around inside W. And so D of G on W is inside W. And the sense in which it's reducible is this. You can basically take, if you have a proper invariant subspace, then when you look at the representation of the group, it looks like this. D of G will look like this. It'll be some sort of D1 of G, 0, 0, D2 of G. So you can, it's equivalent to some matrices that have this block diagonal form. That's what we call reducible. And it's completely reducible if it's equivalent to a representation that's totally block diagonal. So this one is completely reducible in this particular case. There's a deep theorem that I'll just mention in quantum mechanics. First of all, a symmetry transformation. The symmetry transformation means that states go from psi to psi prime, and their inner product, absolute value squared, is the same thing. Looks like that. And so in quantum mechanics, we have rotations, translations, so forth, are such that you have. Oh, I actually did this wrong, so I screwed up here. This should be phi, and this should be psi. Okay. Otherwise, we're talking about something complicated. Now, Wigner showed, so this is the definition of a symmetry. Wigner showed that whenever you have a symmetry in quantum mechanics, you can either represent it by unitary operators U of G that are unitary and linear. And so those are the normal operators that we use. Or by ones K of G that are anti-unitary and anti-linear. So these are very, very spooky, and the only case I know of is when you were involved with time reversal. You know that if two operators commute, in particular if they're, then we say they're compatible, and a set of, I should have mentioned Hermitian here, but anyway, let me put that in. If you have two Hermitian matrices that commute, then you can diagonalize them simultaneously. In fact, actually, let me see, I bet if you have two operators that commute, whether or not they're, oh yeah, Laura, let that person in. Okay, now there's some of this stuff, it gets a little technical, and we've done it in quantum mechanics. I think I'm going to skip to Lie algebra, since I'm going to just focus on continuous groups here. So I'm going to switch now to Lie algebra, and the simple way to talk about Lie groups is to talk about the group in the vicinity of the identity. And so what we say here then is that these parameters are approximately zero. And so we're talking about the representation for the parameters being very, very slightly different from 0. So this would be the identity matrix. And we have this fetish in physics departments where we insist that everything be Hermitian. And so if it's not Hermitian, we just factor out an I and make it Hermitian. So we write this the representation of the group element with parameters d alpha, where d alpha is essentially 0, very small. It's the identity plus something linear in d alpha. We factor out an I so that this thing is of course unitary because we're talking about compact groups, and compact groups have finite dimensional representations. So we're going to, this is unitary. If that's unitary, it has to be 1 plus something that's anti-Hermitian. So we write it as 1 plus I times a Hermitian operator. So TA dagger is equal to TA. The d alphas, of course, are intrinsically real, just because we conventionally take our parameters to be real. And then we can say, well, these t alphas have a simple form, or this TAs, I should say, have a simple form. They're minus I times the derivative with respect to alpha A of the representation at alpha equal to 0, which is kind of obvious from the form that I wrote up here. And they're also automatically Hermitian. And what you can then do is you can use the Gram-Schmidt procedure or something else to make them orthogonal in the following sense. You can say that the inner product of two matrices, the natural thing is to say that it's TA dagger TB. So these are matrices. This is the Hermitian conjugate, so it's the transposed complex conjugate. And you say this is equal to some number, but they're orthogonal. We don't make them orthonormal for a reason that will become apparent shortly. And once we know that this is the infinitesimal form, then we can multiply a zillion of these matrices together to get something that's no longer infinitesimal. And in particular, we can say, we can define d of alpha to be the limit of the nth power of d of alpha over n. So for large n, this is clearly something that's of the form d alpha. And that would be the identity plus I alpha A TA over n to the nth power. But this is what we call the exponential. So what we're led then to is this expression for the unitary matrices that represent the elements of a continuous group. Namely, they're exponentials of I times some set of real parameters times some set of Hermitian matrices. And this is called, obviously, the exponential representation, or the exponential parameterization. Okay. Now, the next thing is to work something out, which is sort of a famous thing. Unfortunately, I've written this so small that it's... So let's write e to the I epsilon TB, e to the I epsilon TA, e to the minus I epsilon TB, e to the minus I epsilon TA. Okay, if you multiply those out, and I did this explicitly, and keep everything to second to quadratic order, what you find is that this is 1 plus epsilon squared, the commutator of TA with TB. plus higher order terms, of course. So forth. I'm not actually sure that epsilon cube occurs, but there's no linear term in epsilon. And on the other hand, this thing here is a product of group elements near the identity. They're all near the identity. And so this must be of the form e to the I, and we see it's of order epsilon squared. It must be e to the I epsilon squared, some linear combination, FC AB TC, which is approximately 1 plus I epsilon squared FCAB TC. So let me just, this is actually quite important. This is this funny combination of forward, backward, forward, backward. For an abelian group, this would just be 1. Because you could just move this guy here, and then you'd have 1 times 1. But the product of these has to be some group element very close to the identity. And in fact, we saw that it was differed from the identity by order epsilon squared. So it has to be e to the I epsilon squared times some set of generators. Oh, these things are called generators. It has to be some set of generators because all the elements of the group are of this form. And so it's got to be that. And so now we come to a remarkable conclusion. The remarkable conclusion is that the commutator of any two generators is I times a linear combination of generators. And in fact, these things are called the structure constants. And what you can see is that they, well, I'm not sure what you can see at this stage, but anyway, those are the structure constants. And what we can do next, we run out of space, not quite out of time, but we run out of space. We can get a formula for the structure constants, namely the trace of the commutator of TA with TB times TD dagger. Well, this is going to be IFCAB trace of TC TD dagger. And that is then IFCAB K delta CD, this CD, and so that is altogether IK FD AB. So these structure constants, in other words, are proportional to the trace of a commutator times the adjoint of the Dth generator. And maybe I'll go to the front there and erase the board and try to. This is New Mexico, so the boards always dry very fast. Okay. Actually, maybe I'll just pause for a moment and ask the two of you then, while the board dries, what you'd like to do next. I'll try to do the high points maybe of group theory and try to finish them pretty quickly, and then we'll go to something else. What do you want to go to next? There are all these different possibilities.
Want to talk about general relativity?
Yeah,
We could do that.
all right. The advantage of doing that is that the context of general relativity is tensors and covariant and contravariant things, and that's stuff that that it's good to know. And in fact, I think in many people, it's almost never explained in a physics class, which really annoyed me as a student. And then it's never explained in a math class either. And then, and actually the ideas are very simple. So, and moreover, because it's not explained, and because it's associated with Albert Einstein, everybody gets the impression that this is, too deep for words, and we'll never understand it.
Yeah.
Whereas actually, it's not. That's not true. It's the basic ideas are quite simple and important. So, all right. So we'll skip through tensors when we finish skipping through group theory.
Sure.
All right. Okay. Remember, the rule still holds, though. If you ask a question, you get a candy.
Okay.
Actually, since you answered questions, that works also. So here, let me. Sure. Well, no, you have to be a member of the class or ask a question. Okay, so what we found then is that the structure constants FCAB is equal to minus I over K, the trace of the commutator TA with TB times TC dagger. These are the commutator. These are the structure constants. The commutator is antisymmetric, and so it's obvious that this is equal to minus FCDA. So the structure constants are antisymmetric in the lower indices. Okay, well, we have these representations which are e to the I alpha A TA, and I wrote them this way, and I said to you that that the TAs were Hermitian, and in fact that's only true for compact groups. So over there I was being a little bit sloppy. I had just been talking about unitary groups and orthogonal groups, and of course they are compact. But in general, we factor out the I, and what's left here, if the TAs are all compact, are all Hermitian, then this is a unitary operator. But if some of them are anti-Hermitian, then this is not unitary. And so this would be an appropriate representation for a non-compact. And in fact, for the case of, say, the Lorentz group, we'll find that we have 6 generators, 6 TAs. 3 of them are Hermitian and 3 are anti-Hermitian. The 3 Hermitian ones generate the rotations, and the 3 anti-Hermitian ones generate the boosts. Now, in the case of compact Lie groups, we have something, so if compact, so let me write here compact, then TC dagger equals TC. And so then what we have is that FCAB is just equal to minus I over K. The K depends upon the representation. Trace of TA, TB, commutator TC for compact groups. And in fact, what one can then say, and in the text, I don't think I'll go through this here in class, but in the text we can show that in fact F ABC is equal to FC AB is equal to minus FC BA. This following because the lower indices are always antisymmetric. And in fact, what we can do for compact groups, we can just say it's FABC, which is FCAB, and this is totally antisymmetric. But for compact groups. Okay, so in other words, these structure constants for compact groups totally antisymmetric, and because they're totally antisymmetric, we don't really need to use this complicated notation where one of the indices is raised. But on the other hand, for non-compact groups, we do, because FCAB is, the C does distinguishes the one that comes in with its adjunct. All right, we're basically out of time. So what I'll try to do next time is try to get through let's see, I think we can turn this off.